Welcome everybody. The main goal of this presentation is review the most important work on meta-learning and knowledge graph in order to predict new knowledge from a few samples. First, we introduce some definition and current challenge on knowledge graph, and then we review the most important work on two important tasks of knowledge graph. The first one is knowledge acquisition and the second one is knowledge completion. Also, we introduce some concepts and definitions on meta-learning, and then we survey the most important work on the three different approaches of meta-learning. And then also we survey the most important work on knowledge graph by using meta-learning. Knowledge graph have become a useful representation of knowledge. Knowledge graph can be represented as a collection of triples with one head entity, one relation, and one entity tail. Usually, knowledge graphs are incomplete, so the challenge is predict new knowledge from a very few number of examples of head entities, relations, and entity tails. The conventional approach of machine learning consists of given a training dataset with samples and labels. We train a model, parameterized by theta, where the cost of learning guide optimization. Here, the parameter W is prefixed beforehand. Instead, meta-learning approach consists of learn W from a set of tasks. As we introduced earlier, knowledge graphs have two important tasks, and they also have important subtasks as well. In terms of knowledge graph acquisition, we have entity discovery task, relation extraction, and representation learning, which also involve knowledge graph completion. Entity discovery can also classify it in terms of four subtasks. The first one is entity recognition, the second one is entity typing, the third one entity linking, and the last one entity alignment. Entity recognition consists of tagging entities in a data stream. Entity typing consists of an inferred type of these entities, and entity linking decides which entity in the knowledge graph refers to the entity. Entity alignment consists of fused knowledge graphs. The most important work on entity recognition is an approach which uses word embedding and chart representation, and then use a bidirectional long-term memory approach to classify entities. The main contribution of this work is that they reach good performance by representing words as a combination of a word embedding and a representation of a chart. However, the main drawback here is that they use a dataset without overrepresented entities. On the side of entity typings, we have an important work here as well. They try to learn label embeddings as a set of prototypes. The main contribution here is that they improve accuracy on fine-grained types. However, they need to integrate with other types of side information. On the side of entity linking, we have that current approaches use excessive supervision. However, a recent approach doesn't need supervision at all. They treat relations as latent variables using neighbor mentions. This technique reached good performance. However, surrounding mentions are not easy to access on real-world scenarios. On that direction, one paper, zero-shot entity linking by reading entity description, tried to solve that problem. On the side of entity alignments, semi-supervised approaches have reached good performance. The main contribution of this work is they use entity description to learn embeddings, but the main drawback is that they fail to incorporate new features. For relation extraction, we have 4 methods. First one, distance supervision, generate training data. Convolutional and recurrent neural networks try to learn future representation, graph convolutional neural nets, and attention mechanisms as well, and reinforcement learning train an agent. One successful approach on distance supervision is this paper. Despite that they show good performance, it fails to capture more complicated feature representation, especially in text corpus of different domains. Distance supervision doesn't handle very well noise on text corpus. However, current neural and convolutional neural networks have become a successful alternative. This paper explores a convolutional neural network approach to embed representation and thus reduce noise. One limitation is that they do not consider other levels influence in these pairwise embedding intersections. In order to avoid redundant information, this paper tried to acquire knowledge for graph via attention mechanism. The main advantage of this approach is that they can use this model to complete knowledge graph and also extract relations. But one limitation is that they not perform well in relation paths. Distance supervision method combined with a reinforcement learning approach have reached a good performance by dynamically recognize false positive samples. So far, we surveyed the most important works on knowledge graph acquisition. And now we need to review the most important work on knowledge graph completion. Knowledge graph completion, also known as a link prediction problem, aims to find relations between entities in a knowledge graph. Usually, this task is done under the supervision of existing entities and relations in a knowledge graph. As we reviewed earlier, representation learning is also part of a knowledge acquisition task, but also is involved with knowledge graph completions. So in this section, we review it. At the same time, knowledge graph completion has another task as well. For instance, we have representation learning as a subtask, relational path modeling, and rule-based and reinforcement learning approaches. Consequently, representation learning can be classified on translational distance-based methods, bilinear methods, neural network approaches, and auxiliary information. Translational distance-based method is the first categorization of representation learning methods. They aim to first learn a low-dimensional vector to representation of entities and relation of existing triples. There are several approaches on translation distance-based methods. They are successful in terms of performance, but in recent years, some researchers have identified they cannot deal with relations having multiple meanings. Bilinear methods are another type of representation learning methods. And this paper was the first approach on that, and this paper is based on the idea of neural tensor network. Here, in this idea, each relation is represented by an n matrix, and the score of the triple is calculated by a bilinear map. Several methods are based on this similar idea. Despite bilinear methods have reached remarkable performance, they present some limitations. They offer high complexity, and they fail to infer orthographic properties, and they lack of interpretability as well, but they offer promising directions. One of the promising directions is introduced by the semantic matching energy function. On this paper, they introduce the concept of neural tensor network, which provide a powerful way to model relational information. One paper in this direction introduced a model called ASME, which represents each entity as the average of its word vectors, allowing sharing of statistical strength between the words. Over the recent years, neural networks have reached remarkable performance. One example of this is a joint graph convolutional framework, but they still don't work well when the number of entities grow. Auxiliary information is a useful resource to improve the representation learning. In those models, both take description as an input to these models. Representation learning is also a knowledge graph completion task, but also have two additional tasks: relational path modeling and rule-based and reinforcement learning. Relational path modeling aims to find relation between entities in a knowledge graph. One of the first approaches on that was path ranking algorithm, which infer new relation by random walk inference. Path ranking algorithm doesn't work well when we don't have a path in the graph. Here, this paper tried to solve that problem, but they failed in a certain dataset. One successful approach on rule-based modeling is this paper here. They guide the linear transformation of the embedding by introducing some rules, allowing learn high-quality rules. So far, we surveyed the most successful approaches on knowledge graph completion, which include representation learning methods, relational path modeling, and rule-based and reinforcement learning methods. Also, we survey not only knowledge graph completion tasks, we also survey knowledge graph acquisitions, which include relation extraction and entity discovery. We explored the most relevant and important work on knowledge graph acquisition task, and knowledge completion task. But now we need to move on meta-learning in order to know more about this concept. The main goal of the meta-learning approach is find a W which reduce the expected learning costs across a set of tasks sampled from a distribution of tasks. The meta-training step of learning how to learn W aims at modeling the probability distribution of how to learn given a set of tasks sampled from a distribution of tasks. Recent surveys on meta-learning have proposed many taxonomies of meta-learning, but here we choose this one, which have three approaches. The first one, optimization-based methods. The second one, metric learning. And the last one, model-based methods. Probability distribution of the output given the input has a powerful feature to distinguish these methods. The first one, this is modeled as a gradient descent. The second one as a similarity, and the last one, there is no assumption about that. Optimization methods are configured as hierarchical optimization problem, in which we have an outer optimization contains an inner optimization as a constraint. The first approach on this direction was this paper here. The goal of this model is to use a gradient-based optimization and use a few examples to converge in a few number of optimization steps. The main contribution of this work is this model is compatible with any model that learns through gradient descent. The limitation is that it's expensive because you use second derivatives. One work tried to leverage on this idea by using a reinforcement learning approach by training tribbles with high frequency relations to find relation in a few shot settings. This work offers a remarkable opportunity for improved knowledge graph embedding methods, which could provide more precise and accurate rewards to the reinforcement learning approach. There are recent approaches with similar ideas. Actually, we have two similar papers here. Both offer improvement opportunities such as correct embeddings, which could improve the representation learning. On the other side, metrics-based methods try to represent a function to map the relationship of embedding vectors of the input data. As an example of that, we use a linear regression as a function. This paper here was one of the first approach on this direction. They tried to learn an embedded representation with two-stream network. Another work on this direction is this paper here, in where they try to learn an embedding by an attention mechanism. Leveraging on this idea, this work here tried to learn an encoded vector as an input of the attention mechanism. The main advantage of this work is that they were the first to consider the long-tail relation in the link prediction task. This work used a machine network as well by performing a joint optimization of neural network models. Another direction is prototypical networks for future learning. Here we have two papers based on the idea of the prototypical networks. Finally, we have the last type of meta-learning approach, which is model-based. Here we update parameters in a few training steps by leveraging structures to hold information. One of the most relevant work in this direction is the meta-learning with memory augmented neural network approach, in which they use a retrieval mechanism based on neural Turing machines. Other work is meta-networks, in which use the idea of fast weights. Finally, we have a summary of the future research direction. In the y-axis, we have the meta-learning approaches, and in the x-axis, we have the knowledge graph tasks. Red circles indicates unexplored areas, and yellow ones indicates medium explored research areas, and green ones indicates explored areas.